The following moles and titration question, taken from an ATP O-levels paper, deals with finding the formula of an acid and you have to find X in the acid. So basically the formula is about figuring out how many hydrogen ions are present in the acid. For example, you have HCl. Now this A over here could be any ion. Different acids have different ion. What all acids have in common is this H+1 ion. So we want to figure out whether what is the quantity of X, how many H+1 ions are present in that particular acid. So if you have, for example, HCl has one H. If you take the example of H2SO4, H2SO4 has two H+1 ions, so it's called a diprotic acid or a dibasic acid. Similarly, you can have H3PO4. H3PO4 has three H+1 ions. So we want to figure out whether this acid has one H+1 or it has two H+1 or it has three H+1 ions. The A could be anything. For example, in HCl, the A in this formula could be Cl-1. Or if you're taking the example of sulfuric acid, the A could be SO4 2- ions. Or if you're taking the example of phosphoric acid, the A could be PO4 3- ions. So the basic premise of the question is we want to figure out whether the acid has one H+1 or it has two H+1 ions or it has three H+1 ions in it. Now the question reads that the student try to find the value of X in the formula of the acid by titrating its aqueous solution with aqueous sodium hydroxide. So there's an acid alkali titration. Sodium hydroxide is an alkali, and you're basically titrating an acid's aqueous solution with aqueous sodium hydroxide. And he's given us that S is 0.045 mole per decimeter cube of aqueous solution of the acid. So we have the concentration of the acid and the name of the acid. It's called S. And T over here is another solution. It contains sodium hydroxide and its concentration is 0.120 mole per decimeter cube. So that is also given. And the next part is that a burette is filled with S and a 25 cm3 portion of T was measured into a conical flask. So we're going to show that in a sketch now. So here is my sketch. This is a titrating apparatus. This is the burette with a tap in it. And this here is the conical flask. So the question states that a burette is filled with S. So you're filling this burette with S. So let's write that down. And what is S? S is 0.045 mole per decimeter cube. So it's 0.045 mole per decimeter cube of the solution. This is the acid HxA. S is 0.045 mole per decimeter cube HxA. So the acid is present in the burette. So we're filling the burette with the acid, and the next part is that T is 0.12 mole per decimeter sodium hydroxide. So 25 cm3 of T, portion of T was measured into a conical flask. So we're going to put T in the conical flask, and we're given a specific volume. So you have 25 centimeter cube of T, which is 0.12 mole per decimeter cube. So it's NaOH, T is NaOH, and the concentration of T is 0.12 mole per decimeter cube. So that is T. So that's going into the conical flask over here. So the concentration of both solutions is known. Now, the next part of the question states which piece of apparatus was used for this measurement. He's asking how would you transfer 25 cm3 of NaOH into this conical flask. 25 cm3 portion of T was measured into a conical flask. Remember, to measure and to transfer liquids, a pipette is the most suitable apparatus. It's very accurate for measuring 25 cm3. That's the only, generally pipettes come in 25 cm3 volumes. So that is the only volume that it actually measures most of the time. After this, once this is done, a few drops of methyl orange indicator were added. So you're adding methyl orange over here. So methyl orange, just a few drops now methyl orange indicator were added, and he's asking what color change was seen at the end point. Now remember that methyl orange, initially this flask contains NaOH. Since it contains NaOH, which is an alkali, methyl orange is it's orange yellow in an alkali. So initially the color would be orange yellow because there is an alkali in it. And as soon as you start adding this acid from the top from the burette into this flask, what would happen is that the acid is going to neutralize the alkali, and eventually all the NaOH would get used up. And once it gets used up and you keep on adding the acid goes in excess. You're adding too much acid. If the acid goes in excess, this solution over here would become acidic, and methyl orange would give a red color in acidic condition, and that would indicate that you're now adding too much acid. Now all the NaOH has been neutralized, and if you still keep on adding the acid is going to make the methyl orange red, indicating that you should turn this tap off now. So that is your endpoint. So the color change would be from orange yellow to red. So that would be the color change for methyl orange. In the next part C of the question, the diagram below shows part of the burette with liquid levels before and after each titration, using them to complete the results table and summary. So we're basically titrating using this acid. This acid is falling into this alkali and it's neutralizing it. And we want to figure out what the volume of the acid that's being used. We know the concentration. We want to know what volume of acid actually falls into this alkali. So he's done 3 titrations, first, second and third titration. 3 titrations are done, or 3 separate experiments are done to get more accurate results, because averaging different experiments would improve accuracy. So in the first titration, he's given the picture of the burette. This is the initial burette reading, and this is your final burette reading. And initially the burette was filled to the 0 centimeter cube mark, and after the titration it showed the level had dropped to 22.6 cm cube, which meant that if you take the difference, that's the amount of acid that was actually added into the flask. So I'm going to fill this burette over here. The first burette reading is 0.00 centimeter cube. Remember to take burette readings to 2 decimal places, because that's the accuracy of the equipment. The second or final burette reading shows 22.60 cm cube. So that's 22.60 cm cube. So what is the amount of acid or volume of S that's actually used? It's going to be the difference between the two values. So in this case, it's going to be 22.60. Moving to the second titration, the initial burette reading shows a value of 17.50 cm cube. So that's your initial burette reading that's filled to this mark. So it's 17.50 cm cube. The final burette reading shows 39.70 cm cube. So that's 39.70 cm cube. And the amount of S or acid that's added from the burette is going to be the difference between the two values. So taking the difference of the two values, final minus initial, gives me, using my calculator, the answer that I get is 22. It's 22.20 cm cube. And now moving to the third titration, the initial burette reading is giving you 8.90 cm cube. That's your initial. And your final burette reading gives you a value of 31.30 cm cube. So that's 31.30 cm cube. And taking the difference, the volume of S added in the third titration is going to be 22.40 cm cube. So that's 22.40 cm cube. So I've done 3 titrations and I got 3 separate volumes of S that are being added in the 3 separate experiments when I've repeated the experiments. So in the next part, I now have to take the best titration results. Remember, the best titration results are the ones that would be close together. So these two values are very close to each other. This one is slightly off. So these two would be my best titration results. And the average volume of S that would be used in this titration is going to be the average of my best titration results. So taking the average of these two values, the answer that I'm going to get is going to be 22.30 cm cube. So that would be the the average titration result, and I'm going to put that over there as well. So the amount of acid on average that's being used is 22.30 cm cube. So we've figured out the volume of acid that's being used in our titration. So moving to the next part D of the question, he said that T is 0.120 mole per decimeter cube sodium hydroxide. So calculate how many moles of sodium hydroxide are present in 25 cm cube solution of T. So we already know that the volume of T that's in this flask is 25 cm cube, and we also know the concentration of T, which is 0.12 mole per decimeter cube. So So if you know the concentration and the volume, the formula is for finding moles in a solution would be concentration multiplied by volume. And if you do that, the concentration is known, it's 0.12 mole per decimeter cube, 0.120 mole per decimeter cube, and the volume, that's 25 cm cube in the flask, and you have to convert that into dm cube. So I'm going to divide that by 1000, and the answer for this on my calculator would be, it would be 0.120 into 25, and then dividing that by 1000 gives me 0.003 moles. So 0.003 moles. So that is the amount of NaOH present in this flask. So the amount of NaOH is 0.003 moles, and let's highlight that. That's the quantity of NaOH in this flask over here, 0.003 moles. In the next part of the question, part E, you're now given the concentration of the acid. We already knew the concentration of the acid over here, 0.045 mole per decimeter cube. We also know the average volume that we use is 22.30 cm cube. So you know the volume and you also know the concentration. So he's asking, calculate how many moles of HxA are present in your average volume of S. So we know the concentration, we know the volume, and again applying the same formula, concentration multiplied by volume. Moles is concentration multiplied by volume. The concentration is 0.0450 mole per decimeter cube, and the volume that's being used is 22.30 cm cube. So I need to convert that into dm cube. So I'm going to divide that by 1000. So using my calculator to solve this, the answer would be, it would be 0.045 multiplied by 22.3, and then dividing that by 1000, and the answer I'm getting rounded to 3 significant figures would be 0.001 moles. So that means, and let's write that down as well, the amount of acid is 0.001 moles in this burette. So that is the amount of acid that's being used in the reaction. Moving to part F, now we need to figure out, using your answers to D and E, deduce how many moles of sodium hydroxide react with 1 mole of HxA. So we just need to figure out a ratio of the moles, HxA ratio NaOH, and we already in the previous parts we figured out the moles of NaOH that are being used in the reaction. The moles of NaOH that are being used are 0.003 moles. So you have 0.003 moles of NaOH being used, and the amount of acid that's being used in the titration is 0.001 mole. So you know the moles of the acid and you know the moles of the alkali. Now he's using your answer to deduce how many moles of sodium hydroxide react with 1 mole. So we just need to simply use ratios. So if we had 1 mole, then the amount of NaOH, what is the amount of NaOH that would be needed? Now the ratio is pretty obvious. 0.001 moles of acid need 0.003 moles of NaOH. So it's 1:3. So 1 mole would need 3 moles of NaOH according to the ratio of moles in the titration that we just did. So the answer to this part is 3 moles. And now we need to figure out, the last part is slightly complicated. We know that the acid, HxA, and NaOH, the ratio of the moles is 1:3. So whenever you make an equation, 1 mole of the acid is going to react with 3 moles of NaOH. Now in the next part, he's asking, using your answers to F, deduce the value of X in the formula HxA. So we need to now figure out what X is in HxA. And X is basically how many hydrogen ions do we have in this particular acid. Now one thing that you could do is, and we discussed this earlier as well, the number of hydrogen ions in the acid could be 1, it could be 2, it could also be 3. So I can take examples of this acid. For example, if I can think of HCl, where it's an acid and H has a value of 1. There's only 1 hydrogen, X has a value of 1. Or if X has a value of 2, I can think of another acid which is H2SO4. Or if H has the 3 hydrogen ions, X has a value of 3, then I can think of phosphoric acid. So now what I can do is, I need to figure out whether the acid has one hydrogen, whether it has two hydrogens, or whether it has three hydrogens. So I'm not going to assume this as HxA because that would make things more complicated. I'm going to think of real acids, and I'm going to try and construct equations using these acids. So for example, let's start with what if X was 1? So I'm going to think of the acid where X is 1, that's HCl. And I'm going to write an equation of a reaction with NaOH. And it's going to produce NaCl. And it's going to produce a water molecule. Now, this is a balanced reaction. But this can't be the answer because if you look at the ratio in which these two are reacting, it's 1:1. So 1 HCl reacts with exactly 1 NaOH. But in our reaction, one acid is reacting with 3 NaOH. So this X is equal to 1 cannot be the correct answer. So let's think of X as being equal to 2. And if I think of X as being equal to 2, the acid that comes to my mind is going to be sulfuric acid, which is H2SO4. So if I pick H2SO4, and H2SO4 reacts with NaOH, then it would produce Na2SO4, sodium sulfate, and is +1, SO4 is 2- plus a water molecule. Now to balance this reaction, what I need to do is I need to multiply it because there are 2 Nas over here. There should be 2 sodium hydroxides over here and 2 water molecules. Now if you look at this reaction, you're going to notice that the ratio of the acid H2SO4 and the ratio of NaOH, it's 1:2. So 1 sulfuric acid reacts with 2 NaOH according to the equation, and this cannot be correct as well because in our reaction 1 mole of acid reacts with 3 moles of NaOH. So this is also not going to be the correct answer. X cannot be 2. Now think of X as being equal to 3. If I think of X as being equal to 3, the acid that would come to my mind would be phosphoric acid. So I'm going to take that example, H3PO4. So if I have H3PO4, it's going to react with NaOH. And it would produce Na3PO4 and a water molecule. And if I try to balance this reaction, there should be the 3 sodiums on the right hand side, so there should be 3 NaOH molecules. That would make it 3 water molecules. Now if you look at this reaction, now the ratio is exactly that 1 mole of phosphoric acid is exactly reacting with 3 moles of NaOH, and that is exactly what we wanted, because in our reaction, in our titration, 1 mole of the acid was reacting with 3 moles of NaOH. So if I take X is equal to 3, then I get a balanced reaction in which 1 mole of the acid reacts with 3 moles of NaOH. So this X is equal to 3 would probably be the correct answer. So the answer would be that X is equal to 3. So this here is my answer. And I use a trial and error method to find out what the value of X is. And in the next part, using your answers to F and G, write an equation for the reaction between sodium hydroxide and HxA. So we've already figured out, we did one example where we took phosphoric acid. Now he's talking about writing the equation in now we know that X is equal to 3, so we can, the formula of the acid would become H3A. Now since H is +1, and there are 3 hydrogens, then A would probably be -3. So A would be -3. So I'm going to now easily write a reaction. The only thing I would do is, I already have an example reaction which is over here. The only thing I need to do is this PO4, instead of this using this PO4, replace that PO4 with A. So get rid of this PO4 and replace it with A, because that's what he's doing. We took H3PO4 as an example, he's taking H3A as an example. So the PO4, get rid of the PO4, substitute A. A could be anything. So H3A plus NaOH would produce Na3A plus water molecule. Everything would be exactly the same as the previous equation. Everything would be exactly the same except for the fact that he's taking A as an unknown ion. I took an example where I used H3PO4. So just replace PO4 with A. That's the only difference that there would be. The rest of the equation would be exactly the same. It would be balanced in exactly the same manner. So this is my equation of sodium hydroxide with the acid H3A.